And our first speaker is Srikanth Srinivasan, who's going to talk about low bounds for non-commutative skew circuits.
Okay, thanks. On? Yeah, okay, good. Thanks thanks Rahul. Thanks to the organizers of this workshop for organizing this workshop and for inviting me. So I'm going to talk about arithmetic circuits today, continuing on with Neeraj's talk on arithmetic circuits. The kind of circuits I'm going to talk about, however, are slightly different. They're going to be non-commutative circuits. Okay, so let's just start by defining a few notions, and then we'll get into the results. So what's a non-commutative polynomial? Well, the normal multivariate polynomials that we come across in various algorithms and other courses are usually commutative polynomials in the sense that they come from the commutative polynomial ring. Okay, so we are going to be working over a slightly different ring. So throughout the talk, there'll be some sort of field f that we are operating over. If you're not comfortable with arbitrary fields, just think of them as the reals or something like this, and some set of n indeterminates or variables. Okay, and we are going to be looking at the non-commutative polynomial ring fx, which I denote like this funny left and right bracket. Okay, that's a non-commutative polynomial ring. It's just a polynomial ring where multiplication is non-commutative. Okay, so you have two variables x and y. From a set of indeterminates, x, y, and yx are really different monomials. They don't cancel, for example, if you subtract one from the other. Okay, so in other words, monomials, as far as we are concerned, are just strings over an alphabet, right? So this is just automata theory, really. It's just strings over an alphabet x. Okay, and this alphabet is of size n. And a polynomial is just going to be a linear combination of these monomials. It's going to be a finite linear combination, though it's not clear from this expression. It's a finite linear combination where these coefficients alpha m for monomial m come from the underlying field, say the reals. Okay, so mostly I'll be talking about homogeneous polynomials because usually that's all I'm interested in. So a homogeneous polynomial is just a linear combination of strings, all of which have the same length. That's homogeneous polynomial. Okay, so these are non-commutative polynomials, and we are going to look at models of computation that compute non-commutative polynomials. Those are non-commutative circuits. Okay, so non-commutative circuits look no different from commutative circuits. So you start with a bunch of variables, right? And you add, subtract, and do a bunch of stuff, and then you output a polynomial. The only difference being that the meaning of multiplication is slightly different. You're multiplying in this non-commutative polynomial ring. So for every multiplication gate, I need to tell you, okay, multiply this thing, then multiply this thing, etc., etc. So at every multiplication gate, there's some sort of ordering among the children of that multiplication gate, and you multiply the gates that are going into this multiplication gate in that order. Okay, so that's a non-commutative circuit. Any question about non-commutative circuits? Right.
Are you assuming that the field f commutes with the variables or not?
Right, the field is always commutative. Right, so the field is always commutative.
And commutes through the...
Absolutely,
okay.
Absolutely. Yeah. So it commutes everywhere. Yeah. So think of these variables as, say, matrices over the field. That's the picture that I keep in mind. Okay. Right. So so these are non-commutative circuits. Okay. So why non-commutative circuits? Why would one look at something like this? So there are multiple reasons. Okay. So one thing is a straightforward generalization of why we look at commutative arithmetic circuits. So now, if you have a computational problem that's naturally stated as a multivariate polynomial over a bunch of variables, then most natural algorithms that you'd think of would be arithmetic circuits. This is why we look at arithmetic circuits, right? You want to be adding and multiplying field elements. You don't want to be looking at the bits of the field elements and doing weird stuff, right? So that's why we normally look at arithmetic circuits. Similarly, if you have a problem, a computational problem that's stated as a non-commutative polynomial, as a polynomial over some sort of non-commutative ring, then the most natural algorithms that you think of would be non-commutative circuits. This is the standard reason to look at this kind of stuff. But this is not the only reason. Polynomials that can be written as non-commutative, problems that can be written as non-commutative polynomials are not very common. But nevertheless, these kinds of circuits do occur even in the commutative setting, in the more standard settings that we are all used to. Okay, what's such an example? So I saw this very nice example in a talk by Avi Vigderson, where we just look at matrix multiplication, right? So as far as algorithmic problems go, it doesn't get much more classical than matrix multiplication. So you have two n by n matrices A and B, and you want to compute their product C. Okay, and let's just go back to Strassen's algorithm, which is really one of the first algorithms that we learn in an algorithms course. So what Strassen did in order to come up with, to multiply these two matrices, a very nice algorithm that he came up with, revolved around this kind of decomposition of this matrix product. So C is the product of A and B, and you kind of divide all these matrices A, B, and C into 4 blocks of n by 2 by n by 2 matrices each, right? N by 2 rows, n by 2 columns, and this is the product that you have. And note that these blocks on the C side, C1, C2, C3, C4, they're all functions of the some blocks on this side. So for example, C1 is A1 times B1 plus A2 times B3, where I'm looking at matrix product. And similarly, C2 is, I don't know, A1 times A2, I'm sorry, A1 times B2 plus A2 times B4, etc. Okay. So if I want to compute C1, C2, C3, C4, well, I can write them kind of easily in terms of A1, A2, A3, A4, and B1, B2, B3, B4. Okay. And I can use this as a template for a recursive algorithm in order to multiply matrices. Only if you do this in a kind of silly way, in the obvious way, you won't get any better than the trivial n cubed running time. So Strassen came up with this kind of magically different way. Okay. So this was the way. I mean, we're not going to go into the hows and whys because I don't know. So what Strassen came up with was this way of multiplying, computing C1, C2, C3, C4 in terms of these AIs and BIs in a way that involved only 7 multiplications and a whole lot of additions and subtractions. Okay. And the important thing is that this is 7 multiplications and not 8, which is the trivial thing. Okay. So now you use this as a template for your recursive algorithm, and boom, you have better than n cubed. Okay. And this has been improved upon a bunch of times. But the point I want to impress upon you here is that this is actually a non-commutative circuit for computing C1, C2, C3, C4 in terms of A1, A2, A3, A4, and B1, B2, B3, B4. Right? Because these are actually matrices, so you can't use commutativity when you're coming up with this recursive template. So this is actually a non-commutative circuit for something. But of course, it's a constant size thing. You're computing 4 polynomials in terms of 8 variables. But you can imagine that improved non-commutative circuits, let's say over 100 by 100 matrices or something, can give you a better algorithm. Okay. So this is one reason to study non-commutative computation, irrespective of whether you're actually working over a problem that's purely defined over a non-commutative domain. Even when you want to multiply matrices over field elements, it's interesting to look at non-commutative circuits for something. Okay. All right. So this is one reason to look at non-commutative circuits. There's another reason, and that reason has to do with lower bounds. Okay, so what Neeraj was talking about in the previous talk was about coming up with lower bounds for arithmetic circuits, and this is a significant challenge that has seen over 4 decades of work. Okay, and this is really a hard problem, especially in the commutative setting. We don't have very many ideas for coming up with lower bounds for general arithmetic circuits or even formulas, restrictions of arithmetic circuits, etc. Okay, so the idea is that if you can compute a polynomial non-commutatively, then that's actually doing more than computing the polynomial commutatively. So what do I mean? So suppose I have an efficient non-commutative circuit for some polynomial, say the permanent, then that gives me efficient commutative circuits for the permanent. Okay. So what do I mean by a non-commutative circuit for the permanent? Well, Neeraj defined the permanent polynomial in the previous lecture. So just take the permanent polynomial. So it's a bunch of monomials, right? Sum those monomials, and each monomial you just take the variables in some arbitrary order, your favorite order, whichever one you want. Okay. And that's a non-commutative version of the permanent. Okay, it's a version of the permanent that lives in a non-commutative ring. Okay. Now, if you have a non-commutative circuit that computes this non-commutative permanent polynomial, then just forgetting about the fact that the circuit is non-commutative, just forget about the fact that this is the left child, that's the right child, etc. You get a commutative circuit for the permanent. Okay. So informally, a circuit that is able to work over non-commutative domains that does not take advantage of non-commutativity will always also work in the commutative setting. That's it. Okay. So circuits, non-commutative circuits actually do more. They work over non-commutative domains. Okay. So upper bounds in the non-commutative setting are harder, and therefore lower bounds in the non-commutative setting should be easier. Okay. You're asking for more, so it should be easier to prove lower bounds, and that's the idea, right? So if you can prove lower bounds for commutative circuits, that in fact implies lower bounds for non-commutative circuits. So maybe looking at non-commutative circuits first is a good idea in order to get to commutative circuits. Okay, that's the general line of thinking. Okay, and in fact, this line of thinking has been justified. So whenever one talks about non-commutative circuit, it's essentially in your contract to talk about Nissan's result. Okay, so this is the first big result in this area, right? So back in 1991, Nissan showed that there are explicit polynomials. He wrote down various polynomials, including the determinant, the permanent, and many others, which do not have sub-exponential sized formulas. So any formula, non-commutative formula for computing these polynomials must have exponential size. Okay. So just to recall, what is a formula as opposed to a circuit? Well, a formula is essentially a circuit where there's some sort of structural restriction on the underlying graph. It's a tree, essentially like a directed tree. Okay. So a circuit, well, once you compute something at a gate in a circuit, you can use it however you like. In a formula, that's not the case. You can just use it once, and then you have to recompute it if you want to do it again. That's the difference between a formula and a circuit. And what Nissan showed is that any non-commutative formula, say for the determinant and a bunch of other things that we'll see, must have exponential size. Okay, so it's a nice result. And in fact, his result didn't just hold for formulas, it actually held for a slightly stronger model of computation called algebraic branching programs. I'm not going to define what these are exactly, but the only thing that you need to know is that they're fairly natural and they're kind of algebraic analogs of log space or non-deterministic log space. Okay, so kind of a fairly natural model of computation. And he showed that any ABP computing the determinant, permanent, and a bunch of other things must have exponential size. Okay, so that's Nissan's result. And so this is kind of justifies our line of thinking that, okay, maybe proving lower bounds for non-commutative circuits in general is an easier problem, and that's something we should tackle first before getting to a commutative setting. That's one line of thinking. Okay, so let me state our result. So as I said, Nissan proved lower bounds for formulas, and in fact for a slightly larger model of computation, stronger model of computation that I called ABPs. Okay, and what we want to do is make progress towards this big ellipse here, which is the class of general non-commutative circuits. So we want to come up with explicit polynomials that don't have general non-commutative circuits. Okay, unfortunately, this kind of result we don't really have the techniques for it yet. In fact, the best lower bounds for general circuits that we have in the non-commutative setting match those that we have in the commutative setting. I mean, it's the same bounds. So we don't really get an advantage by moving to the non-commutative setting for general circuits. So for general circuits, we don't even have quadratic lower bounds, general non-commutative circuits. Okay, so what we do is kind of make progress, interpolate, if you will, between ABPs and general circuits by proving lower bounds for what are called skew non-commutative circuits. So skew circuits. Okay, so I'm just going to define this model here and then state our result again. So what's a skew circuit? Well, a skew circuit is a circuit where there's yet another kind of structural restriction on the gates appearing in the circuit. So let me call a multiplication gate in a circuit to be skew, skew, if at most one of its children is allowed to be a large circuit. So when I'm constructing an arithmetic circuit, I'm allowed to use all sorts of previous computations that I've already done, right? But in a skew circuit, if I'm multiplying stuff, I can only multiply one of the polynomials I've already computed by a complicated process, and the others must all be either variables or field elements. So for example, this gate here, it's multiplying something that you've already computed, something complicated in C, with a variable x1. It doesn't have to be on the right, it could be on the left or the right, wherever. Okay. Whereas on the thing on the right hand side, the multiplication gate on top, it actually multiplies two non-trivial circuits. This is not a skew circuit. Okay. So the difference between skew and non-skew is that skew circuits only have multiplication gates of this form. Right? So they must always, every multiplication gate has only one big child, all the other children are leaves, and they don't have any of these non-skew gates. Okay. Any questions about the definition of skew circuits? Okay, right, so the way I've defined this model, it's kind of funny. Why would you look at something like this? So rest assured that in the commutative setting, there are very many reasons to look at skew circuits. Okay, so skew circuits are in fact equivalent to ABPs that I talked about some time ago, and there are a bunch of reasons to look at them. In the non-commutative setting, things are not so clear, but still there is some motivation, and the motivation being exactly this. Skew circuits can efficiently simulate the models of computation that we already talked about. They can simulate formulas and ABPs, so they're kind of sitting in between ABPs and general circuits. And secondly, Nissan, in the paper that I talked about already, also showed that these guys are exponentially more powerful than ABPs. So there are polynomials that have small skew circuits, so that any ABPs for these polynomials must be exponentially large. Okay, and therefore, kind of proving lower bounds for skew circuits is really proving lower bounds on a much stronger model of computation, and this is what we are interested in. Okay, right? And once again, our theorem: there exists an explicit homogeneous polynomial f of degree d, such that any skew circuit for f must have exponential size n to the omega d. Okay, so n is the number of variables, d is the degree. So in some sense, this bound is, it says that the best thing you can do is, the skew circuit can do in order to write down this polynomial is just to write out all its monomials, because that's n to the d size, and this lower bound is n to the omega d. Okay, so these lower bounds can't really get much stronger. Okay, any question about the theorem before I move on to the proof ideas or something like this? Right, all this is non-commutative. Yeah, so if I don't mention non-commutative, so just assume that every time I say circuit, etc., it's always non-commutative. Okay. All right, so here's a kind of ambitious outline for the rest of the talk. So what I'm going to do is outline first this result of Nissan, which proved lower bounds for formulas. Okay. And then I'll tell you how we kind of modify Nissan's framework in order to get lower bounds for skew circuits, because they're very related. Yeah, question?
No, if you use a general circuit, does your thing have a small size general circuit? Or?
Right. So what you're asking is, does F have a small size general circuit? Yeah, very much. In fact, we'll see that it has a circuit with just one non-skew gate. So I mean, it's a okay. So here's our the outline for the rest of the talk. So I'll just talk about Nissan's proof for a while. Then I'll outline my our lower bound for skew circuits. And then at the end, I'll mention an extension of this skew circuit lower bound, which was proved exclusively for the purposes of speaking about it in this workshop. But it's kind of ugly, so I won't get into the details. So okay, good. All right, so here's Nissan's theorem more formally. There's an explicit homogeneous polynomial f of degree d, that any formula for f must have size n to the omega d. Okay, so how does one prove Nissan's theorem? Well, all theorems, almost all lower bounds for large depth circuits in the arithmetic circuit world essentially follow some sort of simple template. And this template goes like this. So it's kind of related to what Neeraj was talking about in the last talk. So there's also a template that we've been trying to follow in the VP versus VNP setting. So if you want to prove a lower bound for a general circuit of large depth, say, formula, the first step in your proof is a kind of decomposition lemma or depth reduction. Right? You want to squash your large depth circuit or large depth formula into a small depth creature with some sort of restriction. So what Neeraj was talking about in the last class was without an exponential blow up. Here it's some other kind of restriction on the small depth circuit that we get. Yes?
Sorry, quick question. You had said Nissan's was an exponential lower bound. Is this going to be just because you're going to use this, or is this weaker than his? Or?
No, this is exactly his. Yeah. So exponential is like, I take d to be polynomial in n, and right. It's not a constant. Yeah.
So you're not proving it for ABP?
Sorry?
You're proving it for a formula, not an ABP?
We'll prove it just for a formula. Well, I won't even prove it for a formula. I just give you the outline, and I won't. You will see that the same proof technique works for ABPs. There's one lemma that I won't go through. Yeah. Okay. So, right. So all lower bounds have this kind of follow the standard template where there's a first step which is kind of a decomposition lemma or a depth reduction lemma which squashes your large depth circuit / formula into a small depth kind of circuit or formula with some structural restrictions. And the second step is kind of a rank argument, a linear algebraic argument of some form in order to conclude the lower bound. Okay. So Nissan's, I think, may have been among the first such results. So let's just go through it. It's very simple. Okay. So here's the decomposition lemma that Nissan proved for non-commutative formulas. Okay. So before I state the lemma, I just need to make a small definition, and then I can state it. So suppose I have a homogeneous polynomial p of degree d, right, non-commutative polynomial. I'll say that p is a DE product polynomial. It's a DE product polynomial if it can be written as the product of a degree E polynomial and a degree D minus E polynomial. Okay. So p is the product of q times r in that order. Q is on the left, r is on the right. Q is degree E, r is degree D minus E. Yeah, everything is homogeneous. So q is homogeneous, r is homogeneous, etc. So this is a product polynomial, a DE product polynomial. Okay. So here's Nissan's decomposition lemma in terms of these product polynomials. He said that if a homogeneous polynomial of degree d has a formula of size s, then for any e less than or equal to d, so e is a parameter that you can choose whatever you want, right? For any e less than or equal to d, f is the sum of only polynomially many in s product polynomials with these parameters, right? So in other words, f can be decomposed as summation over I pi, where each pi is qi times ri, the degree of qi is e, the degree of ri is d minus e. Okay, right? Okay, so notice that this kind of looks like a small depth circuit, right? It's a sum of products of low degree polynomials. It's just not a small circuit. The only thing you have is you know exactly the degree of qi, exactly the degree of ri. Okay. So it turns out that there is not much to the proof of this lemma. I'm not actually going to go through it. So a similar thing is true for ABPs as well. The proof is kind of by induction on the structure of the formula. Okay. And it actually also holds in the commutative setting. So there's nothing special about this lemma as regards the non-commutative setting. There's a similar lemma in the commutative setting. What is special is that you can use this characterization in order to derive a lower bound, and that's true only in the non-commutative setting. Okay. So let's try to understand the second phase of Nissan's argument, which is the rank argument, the linear algebraic phase. Okay. To understand this, let's try to ask ourselves the following question. So I just defined these notions, these product polynomials in the previous slide. In what sense are these product polynomials special? Okay. So the reason we want to answer this question is because our function, the thing for which, the thing that has a small formula, it is a sum of a small number of product polynomials. So if we understand in what sense product polynomials are special, maybe that will help us come up with a polynomial that cannot be written, decomposed in this way. Okay. So let's just try a very special case of what I'm talking about. So instead of looking at general DE product polynomials, let's look at 2-1 product polynomials. So these are quadratic polynomials that can be written as a product of two linear functions, nothing like this. Okay. So suppose I have summation alpha I xi times summation beta j xj. This is a sum over all ij of alpha I beta j xi xj. Okay. So suppose for now that I gave you a polynomial that kind of looks like this. So it's just some linear combination of xi xj, and I asked you, is this a 2-1 product polynomial? Would you be able to tell? Right. So there are multiple ways one could answer this question. It's quite easy to answer actually. One way is to actually just set up this system of linear equations. Can I find alpha I beta j such that alpha I times beta j is equal to the coefficient of xi xj? But a conceptually nicer way is to look at the following matrix. Right? So for any polynomial p of degree 2, let me set up this matrix. The rows and columns of this matrix are labeled by the variables x1 to xn. And in the ijth position, in the row corresponding to xi and the column corresponding to xj, I put in the coefficient of the monomial xi xj in my polynomial. Okay. This is a matrix I can define for any quadratic homogeneous polynomial, and that's what I'm looking at. Okay. So the observation is that if M is a 2-1 product polynomial, this matrix is rank 1, right? And in general, if it's a sum of a small number of 2-1 product polynomials, it's going to be a small rank matrix, right? And that's essentially the idea behind the lower bound. Okay. So let me just do this in slightly more detail. So if I have a 2-1 product polynomial and I define the matrix for P in this particular way, you get a rank 1 matrix. That's what's special about a 2-1 product polynomial. More generally, if you have a DE product polynomial, you can write down the matrix where you have monomials of degree E labeling the rows, monomials of degree D minus E labeling the columns. Yeah, the entry corresponding to M1 and M2 is the coefficient of the monomial M1 times M2 in your polynomial. Right? Note that this is an exponentially large matrix, like the matrices that occurred in Neeraj's talk. The number of rows in this matrix is the number of monomials of degree E. That's the number of strings of length E over an alphabet of size n. That's n to the E. And similarly, the number of columns is something like n to the D minus E. It's a massive matrix. Okay. And what happens is that if this is a product polynomial, then this matrix actually has rank just 1. It's a huge matrix with rank 1. Okay. All right. So we are ready to finish off Nissan's proof. Okay. So let's just apply Nissan's decomposition lemma with a particular choice of E, right? And we'll take E to be d by 2 or something. It's a very simple choice. The decomposition lemma of Nissan tells us that if a polynomial f has a formula of size s, then it is the sum of polynomial in s many d by 2 product polynomials. Right? The rank argument that we saw tells us that for any product polynomial, for any of these d by 2 product polynomials, the rank of this matrix, the matrix where the rows are labeled by monomials of degree d by 2, the columns are labeled by monomials of degree d by 2, this is going to be a matrix with rank 1. In particular, the rank of the matrix corresponding to f, the polynomial that has the small formula, is at most polynomial in S. Okay. So note that this is an exponential size matrix. Right? It's an n to the d by 2 cross n to the d by 2 matrix. Huge matrix. Rank almost at most polynomial in S. So suppose I chose a polynomial f, which is actually full rank. Right? And this matrix is completely full rank. Then it would have rank n to the d by 2, and this would give me a lower bound of something like n to the omega d. Right? This would give me the claimed lower bound in Nissan's theorem. Okay. So the only thing I have to do is give you an f where this is full rank, and now you can come up with one yourself. So it's very simple. So I just have a square matrix that looks like this, and I want a matrix. I want an f so that this matrix has full rank. Okay. It's very simple. So for example, I could choose f so that this matrix is the identity matrix. and that would give me a nice polynomial. This thing is called the lifted identity polynomial. So I sum over all monomials of degree d by 2, m times m square. Okay. So for every m here, for every m1 here, there's a 1 exactly when m2 equals m1, and otherwise it's 0. So I just get the identity. Okay. So this one has no formulas of size less than n to the omega d. Here's another one that is useful, the palindrome polynomial. So instead of doing m times m, I'll take m times the reverse of the string m. Okay. Once again, corresponding to every m1 here, there's exactly one m2, says the corresponding entry is 1. Similarly, corresponding to every m2, there's exactly one m1, says that the corresponding entry is 1. So this is not a, well, it's not an identity matrix, but it's still a permutation matrix, so it's full rank. Okay. So we get lower bounds for both of these polynomials. Okay. All right, so what about skew circuits, right? So now let's get to our proof. That's Nissan's proof. How do we go about proving a lower bound for skew circuits? Well, the first thing we need to ask ourselves is if Nissan's strategy works. Okay, so can you show that this matrix that we defined for F, it's low rank if F has small skew circuits instead? Maybe a different technique. Okay. Turns out, however, that this kind of proof idea will not work. Okay, and this had already been observed by Nissan. So he said that no, this kind of thing cannot work for skew circuits. Of course, he didn't care about skew circuits, but we do. So, but he observed something that implies this. Okay, right? So and what Nissan showed is that this palindrome polynomial that we saw on the previous slide actually has small skew circuits. Okay, and there's a simple exercise about skew circuits. We just think about it. Kind of construct the palindrome polynomial using the CFG for the palindrome CFL. Right? Just use the CFG idea, and you can easily come up with a skew circuit for this palindrome polynomial. Okay, so this polynomial has skew circuits of polynomial size. Nevertheless, we saw that m of f is, well, it's full rank. The rank is as large as it can be. So of course, this kind of proof, this proof technique, well, at least as is, does not yield lower bounds for skew circuits. Yeah. So what does yield lower bounds for skew circuits? Well, similar proof ideas. So we have to follow the same kind of proof template. Only the decomposition lemma is a little different. The rank argument is a little different, but things look very similar still. Okay. So let me just spend a few minutes describing the thing to you, and then I'll stop. Okay. So in order to state our decomposition lemma, I need to talk about certain strange products. Okay. So the decomposition lemma of Nissan was really nice. We could write f as a sum of product polynomials. Each product polynomial was just q times r. Really simple. Okay. The decomposition lemma we get here is not so simple. It's not so nice. So we've already given up commutativity, right, for this talk. It's all non-commutative. Now we'll give up associativity. Right? Nothing is sacred anymore. So we just give up associativity. So suppose we have two homogeneous polynomials, q and r, of degree e and d minus e. Let me define the j product of q and r. So what's the j product of q and r? It's going to be a polynomial of degree d. The degrees add up. And to define it, it's easiest to do it with monomials. Okay, so let's say q and r are both monomials. Q is a monomial of degree e, r is a monomial of degree d minus e. So what I do is I break up r into a part of degree j and a part of degree d minus e minus j. Right? So r is a string of length d minus e. I break it up into a part of degree j, part of length j, and a part and the remaining part. And then I kind of just wrap r around q. Okay. That's the product of j product of q and r. It's like this. Okay. Right? So for example, if I had x1, x2, the one product of x1, x2 and y1, y2 would be y1, x1, x2, y2. Right? So I just break up r and then wrap it around, place it around q. Right? So it should be clear from this definition that j can be at most the degree of r, which is d minus e. So that's when this product is defined. Okay? And this is for monomials. How do I extend it to polynomials? Well, I just extend it using distributivity. Okay? So suppose I have x1, x2 times the sum of two monomials. I just break up the product with the sum as a sum over products, and I just multiply out. Okay. So in terms of these products, I can tell you what the decomposition lemma for skew circuits is like. Okay. Right. So let me define P to be a DE product polynomial. If it's the J product of a degree E polynomial and a degree D minus E polynomial, where J can be anything. Okay. It's a J product of Q and R, where J could be anything between 0 and D minus E, which is the degree of R. That's a product polynomial. Previously, our product polynomials were very nice because J was always 0, because Q was always on the left of R. Yeah. Now Q could be on the left of R, Q could be on the right because J could be D minus E, but it could be somewhere in the middle as well. Okay. So that's a J product. Okay. And this is the decomposition lemma for skew circuits. A homogeneous degree D polynomial has if it has a skew circuit of size S, then it's the sum of polynomially many in S D E product polynomials of this form. Okay. So that's the decomposition lemma. So you can write F as a sum of polynomials. Each polynomial is Qi times Ri, but the product is some Ji product, and we have no control over this Ji, unfortunately. In the skew circuit, in the formula case, Ji was always 0, so we had control over it. Now Ji could be anything, right? So, but that's all we have. Okay, so it's slightly different. Nevertheless, the claim is that we can use this in order to come up with a lower bound. Okay, and how do we do that? Well, right. So the proof of this lemma, again, this is something I'm going to omit. It's a kind of an induction on the size of the circuit. It turns out that something very similar had already been observed by Rubesh, Vigdison, and Yehudeoff. Okay, so they were trying to come up with such a lemma for general circuits. Turns out that if you take their proof and kind of specialize it to the skew circuits that we're interested in, this is what pops out. Okay, the difference between this lemma and what they get is that we have control over this E parameter. Yeah, and that's going to be crucial. So we get to choose exactly what E is, what the degrees of all these Qis are. That's something that we can choose. What we cannot control, and this will turn out to be the only problem, is that what these Jis are. Well, that's the difference from the formula case. Okay. All right. So how do we use this characterization in order to come up with a lower bound? Well, so suppose I start with, again, let me ask myself the question, what is special about product polynomials? Yeah. In what sense are they special? Is there some rank sense in which they're special, like in the formula case? Okay. And the answer is yes, very much. Yeah. So very similar to the formula setting, there is a matrix that you can write down which has rank 1 if you're looking at a product polynomial. So what's this matrix? Well, the matrix is very simple. So previously, when we are looking at degree, the J equals 0 case, the rows labeled the monomials corresponding to the first E locations, the columns labeled the monomials corresponding to the last D minus E locations, and in the M1, M2 entry, you have the coefficient of M1 times M2 in that order. Right? Here, the product itself is a little different. So, right, so the column, the monomial that labels the column, you first break it up, just like in the J product definition, into a monomial of degree J and a monomial of degree D minus E minus J, and you're looking at the coefficient of this monomial in the polynomial, the coefficient of the J product of M1 and M2. Okay. So once you look at this, so let me define this matrix to be Mj of P. So for any polynomial P, this is the matrix Mj of P. It's quite easy to see that if P is a J product, this matrix has rank 1. Okay, it's nothing special to it. It's just the same argument.
But you have a matrix for every J.
I have a matrix for every J. That's the thing, right? Yeah. So as Prahlad is pointing out, we have not just defined one matrix here. There are something like D minus E many matrices because J could be anything from 0 to D minus E, right? So what we can say is that for each product polynomial that crops up in our decompositions, one of these matrices is going to be low rank, but we have no control on which one. Right? It could be any one of them, but one of them is guaranteed to be low rank. Okay, and that's the only technical issue really that comes up in looking at the lower bound. Okay, so let me just go through it and then pretty quickly we'll be done. So let me just choose parameters. Okay, so I take E in my decomposition to be 3D by 4. Okay, which means that the polynomial that I'm looking at, if it has a small skew circuit, it can be broken up as a sum of small number of product polynomials where this E is 3D by 4. Okay, so these product polynomials can look like this. So for example, I could have a product polynomial that looks like this. Right? This is exactly what happens in the formula setting, and in this case, I know that the rank of M0 of this product polynomial is 1. But I could also have a product polynomial that looks like this because J could go all the way to D minus E, in which case Q would be right multiplying R, in which case the rank of this matrix would be 1, not the rank of M0. Right? But I could also have some intermediate cases where the rank of some other matrix could be 1. Yeah, so all these different matrices, one of them is guaranteed to be of rank 1 for each polynomial, but it's not that the same matrix works for all of them. So you can't just add up the ranks. Okay. So what do we do? Which among these MJs do we choose? Well, it turns out that we don't choose any of them. Okay, so we choose a slightly different one. We consider the following matrix. So for example, in M0, the rows correspond to the first 3 D by 4 locations in the monomial and the columns to the last D by 4. Similarly, in MD by 4, the rows correspond to the last D by 4, the columns to the first D by the last 3 d by 4 and the columns to the first d by 4. But in the matrix that we actually look at, the rows correspond to a middle segment of length d by 2 and the columns to segments of length d by 4 on each side. Okay. So what can we say about the rank of this matrix with respect to these polynomials, these product polynomials? It turns out that we cannot say that the rank is 1, but we can say that the rank is not too large. Okay. So it's still exponentially large, it's n to the d by 4. But note that this is an n to the d by 2 cross n to the d by 2 matrix. So it's a matrix, square matrix with n to the d by 2 rows and columns. So the maximum rank is like n to the d by 2, but still these matrices only have rank n to the d by 4. Okay, and that's the source of the gain. So these matrices are not low rank and they're not rank 1 anymore, but they're still low enough rank that we can use the same strategy and derive our lower bound. Okay. So actually once I tell you this fact, it's not very hard to prove. Yeah. Just leave that as a small aside. And once you have this fact that every product polynomial has small rank with respect to this matrix, then you can say that if f has a skew circuit of small size, its rank with respect to this matrix m prime is at most polynomial in S times n to the d by 4. If on the contrary we choose our f so that this matrix has as large a rank as possible, right, which is n to the d by 2, this will give you a lower bound of n to the omega d. Okay. So the only gain being, so the only thing is that we don't get that these are rank 1, but they're still small enough for us to derive our lower bound. Okay, that's the main observation.
How is it n to the d by 2 translate to d by 2? I mean,
it's because the number of, so the columns correspond to, right, so columns are bringing together the monomial in the first d by 4 and the last d by 4. That's still a monomial length d by 2, right? So you have monomials of length d by 2 labeling the rows, monomials length d by 2 labeling the columns. So you have n to the d by 2 cross n to the d by 2. Make sense? Okay. All right, so to wrap up, I just have to give you an explicit f such that the rank of this matrix is actually full. Okay. And there are many f that you could come up with. You could come up with your own. But here's an interesting one. You just look at the square of the palindrome polynomial we were looking at earlier. Okay. So you take the palindrome polynomial of degree d by 2 now and just square it. That's a polynomial of degree d. It turns out that if you stare at this polynomial enough and just look at the matrix that we were looking at on the previous slide, that's actually full rank. Okay. And the reason is again the same. It's a permutation matrix because what's in the middle d by, this should be d by 2 here. What's in the middle d by 2 kind of determines what's outside, and what's outside determines what's in the middle d by 2. Okay. So this has a trivial, so as I said, the palindrome polynomial has a skew circuit, and therefore this thing is just the product of two skew circuits. So this is a polynomial that's easily computable with just one non-skew gate, but still it requires exponential size when it comes to being computed by skew circuits. Okay. All right, so I just want to mention one brief extension and then I'll close. So as I said, we now have lower bounds for skew circuits, but the proof that I gave you actually tells you something more, right? The polynomial for which we can derive a lower bound, for which I derived a lower bound, is something that has very small skew circuit. I'm sorry, it has very small circuits with just one non-skew gate. So you can ask yourself, can I prove a lower bound for skew circuits with a small number of non-skew gates and things of this nature? Okay. So in order to do this, let me come up with let me tell you a definition. So let me define the non-skew depth of a circuit to be the maximum number of non-skew gates on a path from the output gate to a leaf. Okay, so on any path from the output gate to a leaf, what's the maximum number of non-skew gates you encounter? That's the non-skew depth. Okay, skew circuits are just things where non-skew depth is 0. Okay, it turns out that the proof techniques that I told you about can be used to get the following pretty strong extended result, which is you can come up with super polynomial lower bounds for any circuit with a skew depth is little o of the degree. Okay, it's not very different. And it turns out that if you can get lower bounds for skew depth, non-skew depth d, then that's just lower bounds. I mean, so then it's not a restriction anymore. Yeah? And the proof idea is more of the same. So you have to, your matrix has to be a little more involved, your decomposition lemma is a little more involved, it's iterated, etc. It's ugly, but it's similar. Okay, so summarize. So as I said, Nissan's result gave us an exponential lower bound for formulas. It didn't work for skew circuits. We have an exponential lower bounds for skew circuits using, well, similar ideas, but slightly different technically. Yeah, and the argument even extends as long as your non-skew depth is kind of small, non-trivially small, right? And the question is, can you push something like this for general circuits? I'll stop here. Thanks.
time, let's keep questions for lunch and